Hello everyone. In my last lecture, I talked about the relationship between Galileo's work on projectile motion and Newton's work on projectile motion, which he describes in the beginning of chapter 23 of A Student's Guide to the Great Physics Texts, which is in book 1 of his Principia. Now I'd like to move on to the topic of collisions. This is something that Newton spends a bit of time talking about in this chapter, so I'd like to give you an overview of his approach. So when Newton describes collisions, he considers an experiment, which he actually carries out, where he hangs two balls from the ceiling by strings. He calls this ball A, hanging from a string, and a smaller ball B, which is also hanging from a string from the ceiling. And what he does is he pulls these back to different heights, and then he releases them, and they swing forward, they collide, and bounce off of each other. And he wants to ask the question, are all of the things that he said about conservation of momentum in fact true? So that's the question he's asking. So here's the question. Is momentum conserved during a collision? During the collision of balls A and B. And in particular, is the momentum that is lost by ball A the same as the momentum gained by ball B during the collision? Or conversely, is the momentum that is lost by ball B the same as the momentum gained by ball A during the collision? I'm not going to go through his experiment in detail, but I want to outline how he approaches this. So first of all, in order to know what the momentum, so to know the momentum of each ball, you have to know both its mass and its velocity. So you might imagine he massed or measured the mass of A and B, and he had to measure the speed of each ball. And he had to measure the speed just before the collision and just after the collision. How did he measure the speed of each ball before the collision and the speed after the collision? Well, he deduced it from the height. For example, if you pulled this ball up to a certain height, to this point right here, then it was fairly well known at this time what speed it would acquire on the way down from that height. And likewise, if you pulled this ball up to some height, you could deduce the speed that it acquired on the way down. So he could determine the speed, of each ball before the collision from the initial height of each. I won't go into details of how he did that, but you might imagine that that's possible from the initial height of each. And then that will tell you the speed just before the collision. If you know the mass, you could figure out, for example, the momentum of ball A before the collision. And likewise, if you knew the initial height of ball B, you can figure out its speed just before the collision. And if you know its mass, you can find out the momentum of ball B just before the collision. Well, how does he find out the momentum after the collision? Well, when they hit each other, they're of course going to bounce back up, and how high they get tells you how fast they must have been going just after the collision. So he can determine the speed after the collision by measuring the height that each achieves. Right? So if you know that after the collision, ball A swung back up to this height, and after the collision, ball B swung back up to this height, for example, or some other value, you could determine what speed it must have had just after the collision so as to achieve that height. Now there's a complication here, and that is that he is not doing this in a vacuum. There is in fact air resistance. And so the balls, even if they're going the same speed before and after the collision, they're not going to get back up to the exact same height because there's going to be a drag force that's preventing it to do so, from doing so. So Newton spends a bit of time trying to explain how he accounts for drag. And again, I'm not going to go into the details of this. He spends quite a bit of time trying to explain this. But the point is that he needed to account for drag. And even when doing that, so he had to kind of do a correction for the drag, but he found, and this is on page 279 and page 280, that having made these corrections for the drag, that momentum was conserved, at least to within his experimental uncertainty, at least to within how carefully he could measure the heights of those balls. Okay, so that is the experiment that Newton did to try to verify whether or not this law of conservation of momentum holds, as he had been describing in chapter 22 in the previous chapter. We did this in a laboratory, not using pendula, but we used carts moving along a track. We used a motion detector to measure the speed before and after the collisions, and we were able to study whether or not momentum was conserved during the collision. Okay. Now, I want to talk a little bit more about the conservation of momentum. And I want to remind you of a problem that we ran into. So recall the problem, or one of the problems that we encountered. So that we encountered when first considering the conservation of momentum back in chapter 22. And the problem was that there are many, and in fact an infinite number of outcomes of a collision that are consistent with the law of conservation of momentum. There are an infinite number of outcomes of a collision that are in fact consistent with the conservation of momentum. Okay, so remember when we talked about this, we used this example, well, a similar example. Let me remind you of what I'm talking about here with this example. So let's suppose that we have a ball that has a mass of 2, and it is moving to the right with a speed of 2. That might be, let's say, 2 centimeters per second. And we have another ball, a smaller ball or a less massive ball of mass 1, moving to the left with a speed of 1. So this is going to be our case 1, okay? And this is before the collision. And of course, you know, they are going to collide. And then after the collision, there are several different outcomes that could occur that in fact conserve momentum. So for example, if these two balls stuck together, so here's ball 2 stuck to ball 1, and they are both moving in this direction. Well, let me write down some equations here. So this is before and this is after. So before the collision, what is the total momentum of this system of two balls before the collision? Well, it would just be the momentum of ball 2, which would be the mass of 2. So let me write this down. The momentum of ball 2 plus the momentum of ball 1, right? And what's the momentum of ball 2? It's 2 times 2, which would be 4. I'm going to write plus 4 because it's moving to the right, and I'll call the positive direction to the right. And the mass times the velocity of this one will be 1, but it's moving to the left, so we'll say minus 1. So the momentum of this system would be plus 3. Okay? What about after the collision? Well, let's suppose this has a mass of 2, this has a mass of 1, they're stuck together and it's moving to the right with a speed of 1. What is the total momentum of the system after the collision? Well, it's going to be the momentum of ball 2 after plus the momentum of ball 1 after. And it would be, there, since they're moving at the same speed as 2 times 1 is positive 2, plus 1 times 1 is 1. So the momentum after the collision is plus 3. So momentum is in fact conserved in this collision. Okay, but here's the point, is that there are other outcomes that are also consistent with the conservation of momentum. So again, if you have this ball of mass 2 moving to the right at speed 2, and it collides with ball 1, which is moving to the left with a speed of 1, once again, the momentum before the collision is going to be equal to plus 3. I'm not going to write all the same stuff again because it's redundant. And then after the collision, let's suppose that ball 2 is sitting still. It loses all of its speed, and ball 1 is now flying at a higher speed to the right. It's got a speed of 3. Well, what's the momentum of this system of balls after the collision? Well, it's going to be the momentum of ball 2, which is going to be 0, plus the momentum of ball 1, which is 3. So once again, we have a momentum of 3, right? So here we had a conservation of momentum. And once again, here we have conservation of momentum. So the question is, which of these two outcomes actually happens in nature? After all, they are both consistent with the law of conservation of momentum. There seems to be some ambiguity here. We have no way thus far of deciding which one actually happens. And let me just do one more example for good measure. Okay, so again, we have the ball of mass 2 moving to the right with a speed of 2. It collides with a ball of mass 1 that is moving to the left with speed 1. Once again, the momentum of the system before the collision is plus 3. And then let's say after the collision, ball 2 is moving leftward with the speed of 2, and ball 1 is moving rightward with the speed of 7. Well, what's the momentum of the system after the collision? Well, this one has a momentum now of -4, and this one has a momentum of +7. So once again, we have a momentum of 3, and momentum is conserved. So here I have given 3 possible outcomes of the exact same initial conditions. And by simply invoking the law of conservation of momentum, we are not able to discern which of these will actually happen. I've given you 3 here, but of course there are, in fact, an infinite number of possibilities of the outcome of this collision that are consistent with conservation of momentum. So here what I've done is I've teed up this problem, and in the next lecture I'm going to explain how one can realize the actual outcome of this collision, and so I will stop right here.